Hello, my name is Ruth Whittington, and I'm the Riparian and Wetland AIM Data Analyst and a Wetland Ecologist with Colorado Natural Heritage Program. The following presentation will cover an introduction to wetland soil characteristics, including soil basics such as color and texture, as well as common biogeochemical processes that distinguish hydric soils from upland soils. You can follow along in Appendix M of the Field Protocol for lentic, riparian, and wetland systems. Soils provide a record of the longer-term history of a site. While hydrology and the vegetation that depends on it can change within several years, soils change much more slowly. By digging a soil pit, we can find signs of past and present hydrologic regimes, as well as major disturbances. Take, for example, this AIM site sampled in 2019 in western Utah. The site was located on top of a spring marked on topographic maps, but when walking around the site, there was no signs of surface water. The soil surface was dry. The vegetation was a mix of mesic species and wetland species. However, the soil pit showed thick organic soils down as far as the shovel could reach, suggesting the site must have been saturated for most of the growing season in the past. This demonstrated that the site had likely dried down in its recent history, leading to rapid decomposition of the organic soil and these massive cracks in the soil surface seen in the lower picture. When we look at soil pits, we're often looking at the only record we have of the hydrologic history. We just have to be able to read it. To that end, I'll first go through some of the basic building blocks of soil color and texture. We'll then return to discuss how wetland soil processes influence these characteristics. The first characteristic I'll discuss is soil texture. Soil texture refers to the proportions made up by different size classes of mineral soil particles and is determined by the parent material and degree of weathering that has occurred. All mineral soils are made up of the constituents that are divided into three size classes: sand, silt, and clay. In addition, there may also be some coarse fragments larger than 2 millimeters, such as stones, cobbles, or gravel. These may be an important part of a soil profile, but are easily classified by their size. Simple descriptions can be found in your protocol and Server 123 forms, so I will not cover these coarse fragments in detail. Looking more closely at the three size classes, sand is the largest mineral particle, falling between 0.5 and 2 millimeters in diameter. These are large enough to see and feel individual grains. Because of their relatively low surface area to volume ratio, soils with high sand content tend not to hold on to water or nutrients for very long, resulting in well-drained soils. Next, the middle size class is silt, which is between 0.002 and 0.05 millimeters. At this size, individual grains are no longer visible, and the soil will feel smooth and not sticky when rubbed. Finally, the smallest size class is clay, covering any particle smaller than 0.002 millimeters. In contrast to sand, clay has an extremely high surface area, meaning soils with high clay content tend to hold on tight to water and nutrients. When rubbing clay in your hands, it will feel sticky and dense. To give a visual comparison of the relative size of these classes, this image shows how much smaller clay particles are when compared with sand. You can determine a mineral soil's texture based on the relative proportion of these three components. Mineral soils will fall into one of 12 major soil texture classes, as shown in this diagram, the soil texture triangle. For example, if you have a soil that is 40% sand, 40% silt, and 20% clay, you have a loam. Loams are made up of a mixture of size classes. Soils may also have organic components, which are classified in a different way. Soils with high concentrations of organic components will feel greasy and light due to their low density. A soil with 5 to 18% organic matter may be classified as a mucky modified or peaty mineral soil. These soils are still considered mineral soils and should be textured using the 12-class system described on the previous slide. Once the organic matter concentration increases to 12 to 18% or more of the soil by weight, a soil is instead considered a true organic soil. These are textured instead based on their level of decomposition, which we will discuss in a moment. As a side note, a soil is considered an organic soil or a histosol when 40 centimeters or more of the soil profile is organic. We will classify organic soils into 3 texture categories. The first, fibric organic soil, or peat, is the least decomposed. A fibric soil will be made up of clearly identifiable plant parts and will be clear when squeezed. Next, humic organic soil, or mucky peat, has undergone some decomposition while some plant parts will still be somewhat identifiable. Finally, there is sapric organic soil, or muck. These are the most decomposed and will feel paste-like. These soils will escape through your fingers when squeezed and have very few visible plant parts. The von Post scale, diagrammed in Appendix H of your protocol, goes into the spectrum of decomposition or humification in more detail. The second soil characteristic I want to cover is soil color. Soil color can indicate minerals present, the concentration of organic matter, as well as information about a soil moisture regime. Generally, there are 3 main components of soil with their own distinctive color palettes. First, organic matter tends to have a very dark color. Second, iron oxides have bright orange and red colors. These are what cause southern Utah soils, for example, to have their signature reddish hue. Finally, when both organic matter and iron oxides are missing, we may start to see the color of the minerals themselves, usually showing as a gray color. As an additional note, high salt content can also give soil a white appearance, commonly seen on the surface of playas like the one pictured here. Alternatively, calcium carbonates may also explain white soil color, as seen in areas dominated by limestone parent materials. To show this concept of how minerals and organic matter affect color in another way, here in the upper left corner we have an untreated soil, showing a generic brown color. When organic matter is removed out of this soil sample, we can see that the soil becomes a much brighter orange, as the iron oxides begin to show more strongly. In contrast, when iron oxides are removed, the soil becomes darker as the organic matter starts to show more strongly. Finally, when both the iron oxides and the organic matter is removed, we're left with the color of the minerals themselves. Minerals can have some variation in color as well, but the variation of these leftover minerals is much more muted than the variation caused by the other components. Here we see several different soils, all with their organic matter and iron oxides removed. Soils in the field are described using the Munsell Coloring System, which classifies color using 3 aspects. First, the hue describes the general shade of the soil and goes from 10R as the reddest hue to 5Y as the yellowest. In a Munsell color book, this is indicated by the page itself, as you can see on the tabs of this sample page. Next, the value tells you how dark the soil is, with 0 being the darkest. Value changes vertically on a color page. Finally, the chroma indicates the color intensity, with low chromas having gray tones and high chromas having the brightest tones. These change horizontally across the page. Color is usually said as hue value over chroma. So this color, for example, would be called 5YR 5/8. So using these building blocks of soil color and texture, we can see when we look at a soil profile that soil characteristics change with soil depth, forming layers with distinctive characteristics. Distinct layers are called soil horizons, forming through decomposition and the percolation of organic and mineral constituents downward as water flows down from the upper horizons. Typically, upper horizons tend to be more influenced by biological activity by plants and microbes, while lower horizons are increasingly influenced by the underlying parent material or geology of a soil. Soil scientists will group these layers into a defined set of master horizons seen here, each associated with dominant soil formation processes. Identifying these master horizons takes a lot of practice and experience, so we will not be asking you to know these. Instead, we'll ask you to use soil characteristics to generally distinguish layers in the soil profile. So this brings us back to looking across the soil profile to understand what soil characteristics can tell us about a wetland. When we talk about wetland or hydric soils, the technical definition from the National Resource Conservation Service is that hydric soils are formed under conditions of saturation, flooding, or ponding long enough during the growing season to develop anaerobic conditions in the upper part. What does this mean? Hydric soils are wet, and when soils are wet for long enough time, oxygen becomes depleted and microbes are forced to change their behavior to cope with anaerobic conditions. Under aerobic conditions, oxygen is used by microbes as the final electron acceptor to complete respiration. When the oxygen is gone, microbes will begin to use other soil components in a predictable order, first using nitrates, then manganese oxides, iron oxides, and finally sulfates found in the soil. We can see this below in the redox ladder, though don't worry about the details. But this is where everything we've been talking about starts to come together. When soil microbes use manganese, iron, and sulfate in the absence of oxygen, the chemical properties of these compounds change in ways that we can see and smell. And as getting energy becomes more difficult, decomposition slows down and organic matter builds up in the soil profile. This means that wetland soils change in consistent ways that we can see with our own eyes, or even smell in the case of hydrogen sulfide. These reactions overall are called redox reactions, short for reduction oxidation. Under anaerobic conditions, iron and manganese become reduced, giving them a bluish-greenish gray color called a gley. They are also more easily transported and often become concentrated in the pore spaces of the soil. Once the soil dries out and becomes aerobic again, these compounds are oxidized, showing up as bright colors in the soil. Together, features with these distinctive color patterns resulting from oxidation and reduction reactions are called redoximorphic features. For example, here we see a redox feature in soil pores left behind by roots. This shows signs of regularly fluctuating water table and accompanying cycles of aerobic and anaerobic conditions. Most likely, during a wet period, iron compounds were reduced and moved into the large pores and root zones in the soil matrix with water. As the water table lowered, the same compounds were oxidized again, but this time in concentrated areas. Redox features can appear in several different ways. Here we see redox concentrations in root nodules, but we can also find redox features in soft masses like the lower right pictures, or in models like the bottom middle picture. Alternatively, redox reactions can result in depletions, or areas where iron and manganese compounds have leached out entirely, leaving behind a distinctive light gray mineral soil shown here. This is called a depletion, and it can happen across the soil profile or in an area around redox concentrations, as we see in the bottom photo. In all cases, anaerobic conditions make it harder for microbes to respire, meaning their core functions, such as decomposition, are also slowed down. For this reason, a buildup of organic material is also common in wetland soils. For example, in the spring-fed wetland. Here we can see a site where so much organic matter has built up that the surface is bouncy, as demonstrated by this technician. Overall, we can see that anaerobic conditions that are necessary to define hydric soils are also the conditions that make them distinctive. That gives them common patterns in texture and color that can tell us more about their past history. This concludes the presentation discussing wetland soil characteristics found within the field protocol for lentic, riparian, and wetland systems. Thank you for listening.